Okay, so this is the first video for Chapter 16 on electrostatics. So we're going to consider a couple problems in terms of how point charges are located and their effects on each other, and we might have to use vectors on a couple problems for the rest of this unit. So we'll try to make that as easy as possible. Alright, so in the first problem you can see that we have 3 point charges. We've got a negative charge over here of negative 8 microcoulombs. Remember that's times 10 to the negative 6th power. You know what? Let's go add another significant figure here. So it's negative 8.0. Okay, and then let's say over here that this is 3.0. We want to be careful with our significant figures. I'm getting lax. Microcoulombs there, so positive charge, not quite as big a magnitude, and then another negative charge over here this way, and we've got some measurements in between them. Okay, so negative 0.3 meters means like they're located this far away. Yeah? Okay. So the question is, what is the force exerted by particle 1 on particle, or you know what, not just one of them. Let's consider particle 3 over here, and let's just say basically what's the net effect of these other two charges being in this situation. So what's the net charge on particle 3 because of the other two charges, excluding anything else that might be going on. Okay? So first I thought we'd look at the book's notation, and then in the next problem I'm probably going to just ignore the book's notation. So you can do it either way. So if they say F sub 3 sub 1, what does that mean? You read that as the force exerted by particle 1 on particle 3. I always have trouble with this notation, so I don't know how much we're going to use it for the rest of, but we'll just do it this time. So notice the by part comes second, so 1 is the guy that's kind of acting on 3 in this case. So let's keep that in mind, okay? So this says the force exerted by particle 1 on 3. So we're going to use Coulomb's law and just plug in. So K, remember, is just that universal constant. Remember, sometimes you use the other formulation for the constant in Coulomb's law. We'll probably be using it both ways as we move forward. So the constant is 9 times 10, what is it, to the 9th? And then there's some, it's like newtons per meter squared per coulomb squared to fit this, right? Because you've got like a coulomb squared and stuff, but then there's meter squared would cancel out the radius, so that cancels things out, so you get a force just in newtons. Does that make sense? Coulomb squared on the bottom cancels these out, and meter squared on top cancels the r squared out, so you just get a force in newtons. So anyway, that's what K is. Charge 3, what did we say? We're going to say right there was negative 4 microcoulombs. So negative 4. You know what? Let's just get the magnitude of the charge and worry about direction later. So let's just leave out negative. And you know what? Let's also draw, like for this guy, let's draw that over here. So we've got a negative charge where we're looking. Let's think about what's happening. So the positive charge, which way is it going to go? Is it going to like pull the negative charge in, or is it going to push it away? I think it's going to pull it in. So that's what's going to happen. That's what's going to be this guy, F of 3, 2. So the effective charge 2. And then this negative guy over here, we're going to kind of pretty much ignore the fact that the positive charge is in the way. You don't like add them up or anything. You just do one at a time. And that's going to push it out farther, right? So that's going to be the effect of charge 1, which we're doing first down below. Effect on charge 3 by charge 1, okay? So anyway, we've got those two forces. We'll add them up and see what happens. So let's just do the absolute value first and then worry about directions afterwards with that little diagram. So we've got 4 microcoulombs. So 4 times 10 micro means negative 6, right? Like millionth. And then charge 1 was negative 8. So we're going to have 8 times 10 to the negative 6th coulombs there. And the radius between them, isn't it 0.5? I think so. 0.5, 0.50 I should say, but that's good enough. So let's put that in our calculator. The book got 1.2. Notice significant figures. They're keeping 2 significant figures because we're thinking of these as all having 2. Okay? Then we're going to do this guy, the attracting force. So again, 9 times 10 to the ninth. Sorry, I'll try to go fast here. Plug in your charges. And we were doing this middle charge, so it's 3 microcoulombs. And the radius between those is 0.2, isn't it? Okay. Just for the heck of it, I'm going to plug this into my calculator this time. Quick as I can. So I got 2.7 even. Wow. Came out nice and even. 2.7 newtons. Okay, so now let's go back and look at our diagram and just check which way we think it's going and stuff real quickly. So which one of these forces is bigger in magnitude? Looks like the one that was attracting in the middle is bigger in magnitude. So let's define our coordinate system. Let's just go standard like x, y. So, oh my gosh, not x9. xy. Yeah, so xy, so that means this is positive in that direction and up is positive, just like we're used to. So if this is 2.7, remember that guy's being pulled backwards, we better consider that as negative. So I'll put a negative in there. And this guy was going this way, so that's going to be positive. So in other words, let's say F net, the net effect of those two charges on charge 3 is to make it go negative 1.5 newtons to the left, right? So essentially it's going to be pulled left if we were to let the situation progress in time. Okay, there's one. So let's look at one where the vectors are not just along a straight line. So let's look at one where they're kind of just out in 2 dimensions. I guess we won't go 3 dimensions quite yet. Well, we could. I mean, it really wouldn't be that much more complex. Just hard to draw. Okay, so let's say we've got a positive charge up here, another positive charge here, and a negative charge there. And we're just trying to figure out, again, we'll call this one charge 3, that one charge 2, and charge 1. Looks like there's more charge in this case. We got like 65 and so forth microcoulombs. So an order of magnitude bigger than last time. But anyway, again, we're trying to figure out what's the net. It says calculate the net charge on Q3 due to the other two charges. So we might have to do some angles this time. But first, notice, I'm not going to do their fancy subscripts. That just bothers me, so you don't have to. So why do I have this red vector up here? Why did I say that's going up? Because if we're investigating this charge and that's positive, opposite, similar charges repel, so it's going to be pushing it up. Opposite charges attract, so that's going to be pulling it in. So that's kind of the idea. I just called them force 1 and force 2 to make it simple. So force 1 is going to be straight up. Let's do that one first. So we go 9 times 10 to the 9th for our Coulomb constant. And then charge 3 is the one up on top, so that's 65 times 10 to the negative 6. And then charge 2 is this guy down here, so 50 times 10 to the negative 6. As long as you keep track of your diagram, it's a lot easier than doing all this fancy subscripts, I think. But anyway, R, what's the radius here? I need to tell you this distance. So, I don't know, let's say they're 30 centimeters apart. So I'll put a measurement there, 30 centimeters. Let's say this is 52 centimeters if we were like measuring it in a lab. So we can figure out that one now, right? So this guy would be the square root of, 52 squared plus 30 squared, and then that'd be in centimeters. Anyway, this radius here is where we were thinking in Q3 and Q2, so it's 30 centimeters, so that's going to be 0.3 meters, right, squared. Okay, so I think that works out to about 330 newtons. Okay, so we've got that one, and let's do the other one. Let's just do the magnitude first. We'll worry about our angles later and so forth. Looks like we've got 30 degrees and a right angle there. But anyway, 9 times 10 to the ninth. Q3 is 65 again. Q1 is the biggest charge, but it's negative. You know what, let's leave that negative off again. I don't think we need it. So goodbye, negative. Worry about that in a sec. And then 0.3 squared. No, 0.3 squared, what am I talking about? So that's where we're going to have to use that distance that we calculated there in green. Let's see what that is. I'm going to put that in my calculator. So let's see, square root of 30 squared, 52 squared. So I got significant figures wise, it's 60.03. Since those other two had two significant figures, we're just going to keep 60 though. Okay? So we'll say 60, so 0.6 squared. Point. Okay, so we throw that in and we get about 140 newtons. Okay, so we've got the magnitude of our two forces. Now let's see if we can draw a little diagram and see what's happening to this guy up here. So maybe I'll make it like purple. So what's happening to this guy up here? So let's bring it over here and think about our actual vectors. So I'm going to do so red. So this other positive charge is going to repel it straight up, right? So that's like its effect is going to be straight up. And then this guy is going to be pulling it straight this way. So overall, if we do like a vector addition, I hope you remember that for vector addition, you like make a little parallelogram. So I think that when those vectors are added, the vector addition is probably going to be out in this direction somewhere like that. If you can see the yellow one, okay. So let's add stuff up and see if we actually do get something like that. Okay, so this one's pretty simple. It's just a y component. This guy over here, though, the effect of charge 1 is kind of split into components. So doesn't it have like a y component down? So we'll call that it's just its y component. You can put f sub 2y if you want. That's probably better notation, but I'm just going to put f sub y. Yeah, let's put f sub 2y. That's probably more specific. And we'll say f sub 2x that way. So let's calculate those. Okay, so f sub 2y, first of all. How are we going to get just the y component of this guy? So we've got f sub 2. How can we break out just its y component? So do you remember how to do that? If you want just its y component, don't you use the sign? Don't you just say like sign? And is it going to be down or up? I think we can see that it's down, so we'll just go negative. And the angle in there, what is the angle in there? If we think about it, let's see. So if we, what angle should we use? So if this is 30 degrees, this guy is 60 degrees. Do we want to use the 60 or the 30? I mean, it's kind of up to us how we arrange this problem. I'm thinking of it as like this guy, so I'm using that angle. Should I draw that bigger off to the side? So here's f sub 2x, and then we've got the, almost keeps the color the same. Then we've got that dashed black line going down to the other charge. And then we could think of this as like f sub 2y, couldn't we? So we really want like this angle right here. So what is this angle right here? If that's 60, isn't this 30? Cool. I think I'm going to do it that way. So you could think about the triangles kind of however you want, but I'm going to do it that way. So I'm going to use the sine. That's the sine, isn't it? Opposite. So I'm going to say sine of 30 degrees times the magnitude. What was the magnitude? 140. Okay, remember the negative is on there because it's going down. Nothing sneaky. So what is that? We punch that in our calculator and we get about, negative 70. Okay, and then f sub 2 x is just going to be this guy, so I think that's the adjacent or the cosine component. It's going to the right. We'll define our coordinate system just like normal, so positive is to the right, so cosine of 30 times its magnitude of 140. And now we've got its components, so negative 70, and this turns out to 120. So we've got the components of that second vector now. So let's find the overall vector, which is the yellow. So yellow is going to be hard to see though. I'm going to use black. So f sub y, the overall vector. Don't we have to do this guy and that guy? So we've got f sub 1 going up, the whole thing, right? Its whole thing is a y. So 330. And then we had part of this other one coming down because that negative charge is trying to pull it straight down a little bit. So that's negative 70. So what do we get there? 260? 270? What am I thinking? Yeah, 260. Gosh. And then x, this charge isn't being moved left or right at all by this charge. It was pure y component, right? But it is being moved that way a little bit, so it's just that 120. So there's its components. If we want the vector from its components, remember we just go the Pythagorean theorem. So we go 260 squared and 120 squared, and we get about 290 newtons. So that's the overall magnitude of the resulting force from those two charges on this guy. So that's what that yellow guy is going out at. Remember, we could calculate the angle too. So if we wanted like the angle from like this angle, we could do that and say the tangent of that theta, let's call it theta. Theta is, what is it, opposite? So opposite would be the y component, so that would be like 260 over the x component of 120. Take the inverse tangent of both sides, and you get theta is about 65 degrees, which looks pretty reasonable from the diagram we had drawn if everything's to scale and stuff. It looks pretty much to scale, so there we go. A lot of problems might say like balance that, like a conceptual example right below it says to balance that charge by adding another charge. So if you needed to like balance this so that the positive charge didn't move by introducing some kind of artificial charge, so we've got it's being pushed out with this yellow direction, you'd kind of have to sneak in a vector that would balance it out in this direction, wouldn't you? So if they specify a certain amount of charge, you could like solve the problem for the other thing in Coulomb's law. You could say like, well, here's the two charges, and you could like use Coulomb's law to balance it. But it would have to, you'd have to add another charge over here. And let's think about it. Would it have to be a negative charge or a positive charge if we wouldn't want this guy to be deflected essentially by these two? I think since that's a positive charge pushing it out that way, I think we'd have to put a negative charge a certain distance over here. Okay? So there's the first video. I will see you next time.